In this video, I'll be discussing the second lab in Physics 2212 on magnetic fields of permanent dipole magnets. Introduction. This lab evaluated the distance dependence of the magnetic field of a bar magnet determined by a cell phone magnetometer app, which was then used with respect to the Biot-Savart law to calculate the magnetic dipole of the magnet. This was then modeled in GlowScript to compare the mathematical model to reality. For this experiment, a magnet was attached to the zero end of a meter stick and aligned west to east, making sure that the magnetometer is near zero in the x direction, far from the magnet. Then the magnetometer inside the phone was located for accurate distance measurements. From here, the procedure evaluated the distance at which the magnetic field was 20, 70, 120, 170, and 220 microteslas, increasing in the x component as the phone moved closer to the magnet. From here, the data could be plotted logarithmically to linearize the simplified Biot-Savart law and determine the exponent of the r term responsible for the distance-dependent relation, as well as the constant term, which was used to evaluate the value of the magnetic dipole that would later be used in the simulation. We find that the n exponent is approximately -3 no units, and the dipole moment is approximately 11.417 amperes per meter squared. The field was also measured 45 degrees off-axis, where the distance was calculated by the spreadsheet for both the horizontal and vertical components of the square, with the measured values corrected for the Earth's magnetic field using public geological data. Displayed on screen is the GlowScript code used for the magnetic dipole simulation, where the full Biot-Savart law was used to model the magnetic field of the bar magnet from the experiment, assuming that the bar magnet behaves like a dipole and does not include the Earth's magnetic field. In the resulting display, 7 vectors at different positions denote the magnetic field around the magnet, with 2 on-axis, 4 perpendicular, and 1 45 degrees off-axis. Notice that the simulation's 45-degree off-axis vector differs from the experimentally measured vector, primarily due to the non-zero z-axis value in the experiment, likely as a side effect of the compensation for the Earth's magnetic field. Discussion. This experiment had several potential points of error, primarily associated with compensating for the Earth's magnetic field, as seen in the discrepancy between the 45-degree off-axis in the model and experimental measures. Moreover, the setup was also difficult to secure in the west-east direction. Lastly, the distance between measurements could have been hindered by the precision of the meter stick as well as the exact location of the magnetometer inside of the phone. What-if questions. What if the setup was not aligned to the magnetic north, but an intermediate angle? In this scenario, the measured values would be the net magnetic field of both the magnet and the Earth's magnetic field, which would have changed the distances at which the microtesla intervals were measured. While this would affect the experimental measurements, the n exponent, k constant, and dipole moment values should still remain the same, assuming the Earth's magnetic field contribution in each direction remained constant. What if you redid the experiment with 2 identical magnets stuck together? In this scenario, the measured magnetic field would be twice the magnitude of a single magnet, thus doubling the k and dipole moment values. However, the n exponent will still remain the same due to the distance dependence of the dipole magnetic field. In conclusion, this lab provided a deeper understanding of the distance dependence of the magnetic field of a dipole, calculating the dipole moment of a bar magnet, and modeling the magnetic field of a dipole using computational models.